psychrometric chart graphically represents the thermodynamic properties of moist air. So this is the psychrometric chart where we can see that the bottom horizontal line represent various values of dry bulb temperature, whereas the vertical line represent various values of specific humidity. This is the saturation curve at which the value of relative humidity is 100%. The curves which are in similar pattern to the saturation curve show the constant relative humidity lines. These thick solid lines represent the constant value of specific enthalpy, whereas these dotted lines represent the constant value of specific volume. That's why they are called as lines of constant specific volume. So this is the actual psychrometric chart where we can see that the bottom line represents the dry bulb temperature values, vertical line represents the various values of specific humidity. This is the line which represents the various values of enthalpy. Also, the lines parallel to the specific enthalpy lines represent the constant wet bulb temperature lines. These are the lines which represent the constant value of specific volume. These are curves which represent the constant value of relative humidity. Now this is one scale known as sensible heat factor scale, which shows the various values of sensible heat factor. So what is sensible heat factor, that we are going to see further. Now what are various psychrometric processes? So starting with sensible heating, followed by sensible cooling, humidification, dehumidification, cooling and dehumidification, cooling and humidification, heating and humidification, heating and dehumidification, and lastly adiabatic mixing of two streams. So first of all, sensible heating. So the heating of air without any change in its specific humidity is known as sensible heating. So there should not be any change in its specific humidity, but there should be increase in temperature. So this is the basic feature of sensible heating. For sensible heating, steam or hot water is passed through heating coil. So this is the diagram where we can see that air is entering at a dry bulb temperature TD1. It is passing over a heating coil where steam is entering at a temperature of TD3. So temperature of heating coil is TD3 and air is leaving at a temperature of TD2. So these are the various temperatures. Now effect of adding sensible heat is that we can see that temperature is increasing. Dry bulb temperature is increasing at a constant humidity ratio or specific humidity value. In sensible heating, the heat absorbed by the air during sensible heating may be obtained from the psychrometric chart by the enthalpy difference H2 minus H1. So 1 to 2 process is the heating process, sensible heating process, where we can see that the value of relative humidity is decreasing from Phi1 to Phi2. Value of enthalpy is increasing from H1 to H2. So that's why heat added can be shown as Q equals to H2 minus H1. During the process of sensible heating, the value of specific humidity remains constant. Now next is sensible cooling. So the cooling of air without any change in its specific humidity is known as sensible cooling. So this sensible cooling process is exactly opposite of sensible heating, but the specific humidity is going to be constant here, just the temperature will reduce. For sensible cooling, refrigerant or cooling water or cooling gas is passed through the cooling coil. So air enters at a temperature TD1, it leaves at a temperature TD2 after passing through a coil or over a coil which is at a temperature of TD3. So this is the effect of removing sensible heat. That means sensible cooling is the process where temperature from TD1 reduces to TD2. So similarly, we can consider 1 to 2 is the process of sensible cooling. Relative humidity increases from Phi1 to Phi2 at constant specific humidity. TD1 it reduces to TD2. So heat rejected in this process can be said as Q equals to H1 minus H2. Now next is about bypass factor, which is denoted by BPF of heating or cooling coil. So BPF is a term, important term related to heating and cooling coil. So it can be considered that 1 kg of air is entering at a temperature TD1. It passes over the coil, which may be a heating or a cooling coil, and X amount of air do not comes in contact with the cooling coil. So the amount of air which is coming in contact with the cooling or heating coil is 1 minus X kg, and air leaves outside the insulated apparatus at a temperature TD2. So TD3 is the temperature of the coil. Now we know that the temperature of air coming out of the apparatus TD2 will be less than TD3 in case it is a heating coil. So TD3 will be more. After the sensible heating process, TD1 will increase to TD2. So still it will be less than TD3. Now for temperature of air coming out of the apparatus TD2 will be more than TD3 in case of a cooling coil. So TD1 will be highest in case of cooling process and TD2 will decrease as a result of cooling. So TD2 will be more than TD3. Under ideal conditions, the dry bulb temperature of air leaving the apparatus should be equal to that of the coil. But it is not so because of efficiency of the coil. This phenomena is represented by bypass factor. So the performance of a heating or cooling coil is measured in the terms of bypass factor. A coil with low bypass factor has better performance. So value of X should be as low as possible for better performance. So now balancing the enthalpies, we get this equation that X into CPM into TD1 plus 1 minus X into CPM into TD3 equal to 1 into CPM into TD2, where CPM is the specific humid heat. So by simplifying this term, we get that X equals to TD3 minus TD2 upon TD3 minus TD1, where X is called as the bypass factor of the coil and it is generally written as BPF. So for heating coil, the BPF should be written as TD3 minus TD2 upon TD3 minus TD1 as TD3 is more, and for cooling coil BPF should be written as TD2 minus TD3 upon TD1 minus TD3. So these are the same terms, just the higher temperature value term is taken at first. Now efficiency of heating coil. So the term 1 minus BPF is known as efficiency of coil or contact factor. So efficiency of heating coil will be 1 minus BPF, and if we replace the BPF with the formula in the previous slide, then we can see that 1 minus TD3 minus TD2 upon TD3 minus TD1. So this will be the term which we will be getting by simplifying. And efficiency of cooling coil will be equal to TD1 minus TD2 upon TD1 minus TD. Now next process is humidification. So the addition of moisture to the air without change in its DBT is known as humidification. So in humidification, only temperature is going to be constant, but humidity is going to increase. So humidification is achieved either by supplying or spraying steam or hot water in the air. So we need to add moisture to the air in humidification process. So effect of humidification or humidifying the air will be that the humidity value will increase from 0.1 to 2. So we can see that. So in humidification, change in enthalpy is shown by the intercept H2 minus H1 on psychrometric chart. The dry bulb temperature of the air during humidification remains constant, therefore sensible heat also remains constant. So we can see that 1 to 2 processes of humidification where specific humidity is changing from W1 to W2, relative humidity is increasing from Phi1 to Phi2, enthalpy is also increasing from H1 to H2, but DBT is constant at this point. So the change in enthalpy per kg of dry air during increased moisture content equal to W2 minus W1 per kg of dry air is considered to cause a latent heat transfer. So now humidification is a process where latent heat is added to the air. So latent heat is given by H1 minus H2, which can be written as HFG into W2 minus W1, where HFG is the latent heat of vaporization at dry bulb temperature TD1. Now dehumidification is the process of removal of moisture from the air without change in its DBT. So process 2 to 1 is the dehumidification process. Now in dehumidification, change in enthalpy is shown by the intercept H1 minus H2 on the psychrometric chart. So 1 to 2 is the process of dehumidification, where we can see that the relative humidity decreases from Phi1 to Phi2, humidity value decreases from W1 to W2, and enthalpy value also decreases from H1 to H2. So this process is of removal of latent heat from the air. So the change in enthalpy per kg of dry air due to decreased moisture content equal to W1 minus W2 kg per kg of dry air is considered to cause a latent heat transfer. So latent heat here will be H1 minus H2 equal to HFG into W1 minus W2. So this is the diagram where we can see all 4 processes. From this point, if we move towards right, then this is heating. If we move in opposite direction, then it will be cooling. If we move upwards, then it will be humidification or humidifying the air, and if we move downwards from this point, then this will be dehumidification or dehumidifying the air. Now what is sensible heat factor? So the heat added during psychrometric process may be split up into sensible heat and latent heat. So the ratio of sensible heat to the total heat is known as sensible heat factor or sensible heat ratio, SHF or SHR, which is given as SHF equal to SH divided by SH plus LH. So where SH and LH are sensible heat and latent heat respectively. So the sensible heat factor scale, as we have discussed previously, is shown on the right hand side of the psychrometric chart. Now similar to SHF, we can write room sensible heat factor RSHF equal to RSH upon RSH plus RLH, where RSH and RLH are room sensible heat and room latent heat. So next is the grand sensible heat factor, which is denoted by GSHF. So GSHF is given by TSH divided by grand total heat, TSH upon TSH plus TLH. Total sensible heat divided by total sensible heat plus total latent heat. Next is effective room sensible heat factor, denoted by ERSHF, given by ERSH divided by ERTH. TH means total heat. Now next is cooling and dehumidification process. So this process is generally used in summer air conditioning to cool and dehumidify the air. The air is passed over cooling coil or through a cold water spray. Now in this process, the dry bulb temperature as well as the specific humidity decreases. So this is the cooling and dehumidification. In cooling, we decrease the temperature. In dehumidification, we reduce the humidity content. So the final relative humidity of the air is generally higher than that of the entering air. So this is the diagram where we can see that the process 1 to 2 is of cooling and dehumidification, where we can see that TD1 is reducing to TD2 during the process and W1 is reducing to W2. H1 and H2 are corresponding enthalpy values for point 1 and 2. So the dehumidification of air is only possible when effective surface temperature of cooling coil TD4 is less than the dew point temperature of the air entering the coil TDP1. So TD4 should always be less than the TDP1, that is dew point temperature at point 1. So then only this process will be possible. The effective surface temperature of the coil is known as apparatus dew point. So in this diagram, the apparatus dew point, which is denoted by ADP, is TD4 temperature at this point. So ADP is the effective surface temperature of the coil. Now in cooling and dehumidification process, we see that the actual process is from point 1 to 2. So in cooling and dehumidification process, actually it is the process which follows the path as shown by a dotted curve in the figure 1 to 2. But for the calculation of psychrometric properties, only endpoints are considered, so only endpoints are important. So thus the process is denoted by 1 to 2, which is combination of 1 to and A to 2. So that's why the Q, that is total heat removed during the process, which is combination of latent heat and sensible heat, is denoted by H1 minus H2. So that's why we can directly write the sensible heat factor value as HA minus H2 divided by H1 minus H2. So the line 1 to 4 in this diagram represents the sensible heat factor line. Next is the diagram where we can see the cooling and dehumidification followed by this point and this line. So which is a combination of cooling and dehumidification. So we get the output as this line. Next process is of cooling and adiabatic humidification. So when the air is passed through an insulated chamber having a spray of water known as air washer, so these are the spray nozzles also known as air washer, maintained at a temperature T1 higher than the dew point temperature TDP1 of entering air, but lower than the dry bulb temperature of entering air, equal to the wet bulb temperature of entering air, then the air is said to be cooled and humidified. So T1 should be equal to TW1 in short. So air enters and then it leaves after passing over the spray nozzles. So since no heat is supplied or rejected from the spray water, as the same water is recirculated again and again, therefore in this case a condition of adiabatic saturation will be reached. The temperature of the spray water will reach the thermodynamic wet bulb temperature of the air entering the spray water. This is the psychrometric process which is shown in the figure. Now this is the diagram which shows that the cooling and dehumidification process is from point 1 to 3 and it follows the path along the constant wet bulb temperature or constant enthalpy line. In an ideal case, that is when the humidification is perfect or humidifying efficiency is 100%, the final condition of air will be at point 3. So if we are considering process 1 to 3, then this is the ideal humidification process. But generally it is not so, and because in actual practice, perfect humidification is never achieved. Therefore, the final condition of air at outlet is represented by the point 2. So 1 to 2 will be the actual humidification process. 1 to 3 will be the ideal humidification. So the effectiveness or humidifying efficiency of spray chamber is given by eta H equal to actual drop in dBT divided by ideal drop in dBT. So which can directly be given as eta H equal to TD1 minus TD2 divided by TD1 minus TD3, which can also be written as W2 minus W1 upon W3 minus W1. Now similarly, when the water is injected at a temperature T1 equal to wet bulb temperature TW1 of entering air, then cooling and humidification by water injection, that is evaporative cooling, can be represented by same line 1 and 2 on the same figure, which follows path of constant wet bulb temperature line. So next is the process of heating and humidification. This process is generally used in winter air conditioning to heat and humidify the air. It is reverse process of cooling and dehumidification. The air is passed over a humidifier having a spray water temperature higher than the dry bulb temperature of entering air. The unsaturated air will reach the condition of saturation and thus the air becomes hot. So this is the process of heating and humidification. So the heat of vaporization of water is absorbed from spray water itself and hence it gets cooled. So water gets cooled and air gets heated. In this way air becomes heated and humidified. So this is the diagram which shows the process of heating and humidification from point 1 to 2. So the actual process is from point 1 to 2 in this curve, in form of this curve. But as endpoints are important, so we consider it as a line 1 to 2. So in this process, the dry bulb temperature and specific humidity of air increases. The final relative humidity of the air can be lower or higher than that of the entering air. So as we discussed that process 1 to 2 is of heating and humidification, which is a combination of two processes, that is from point 1 to A and A to 2. So thus A1 to A is heating and A to 2 is humidification. The total heat added to the air during the heating and humidification process is Q equals to H2 minus H1, which is equal to H2 minus HA plus HA minus H1, which is equal to summation of latent heat plus sensible heat. So directly we can write the sensible heat factor is equals to HA minus H1 divided by H2 minus H1. The line 1 to 2 is known as sensible heat factor line. So this line 1 to 2 is sensible heat factor line. Next is the process of adiabatic chemical dehumidification. So this process is mainly used in industrial air conditioning and can also be used for some comfort air conditioning installations requiring either a low relative humidity or a low dew point temperature in room. In this process, the air is passed over chemicals which have an affinity for moisture, means they absorb moisture. So that's why dehumidification will occur. As the air comes in contact with these chemicals, the moisture gets condensed out of the air and it gives up its latent heat. Due to the condensation, the specific humidity decreases and the heat of condensation supplies sensible heat for heating the air and thus increasing its dry bulb temperature. So this is the diagram where we can see process 1 to 2 is of adiabatic dehumidification, where actual adsorption or dehumidification is taking place from point 1 to 3. So during the process 1 to 3, dry bulb temperature it is getting increased from TD1 to TD3, but the humidity is reducing from W1 to W3. So the effectiveness or efficiency of dehumidifier is given by the formula eta H equals to TD3 minus TD1 divided by TD2 minus TD1. So this is actual increase in dBT divided by ideal increase in dBT. Lastly, we have a process of adiabatic mixing of two air streams. So when two quantities of air having different enthalpies and different specific humidities are mixed, the final condition of air mixture depends upon the masses involved and on the enthalpy and specific humidity of each other constituent masses which enter the mixture. So the process is in such a way that we get the final condition as point 3. So when two conditions from point 1 to 2 are mixed, then we get a combined condition of point 3. So assuming no loss of enthalpy and specific humidity during the air mixing process, we can have mass balance as m1 plus m2 equal to m3, energy balance as m1 h1 plus m2 h2 equals to m3 h3, mass balance of water vapor as m1 w1 plus m2 w2 equal to m3 w3. So these are the various psychrometric processes. Thank you.